All right, hi guys. So my name is Max. I'm one of the SIs for Dr. Maduro's 5A class. And today I'm going to be going over just a couple of things to do with free energy and kind of energy related to molecules in the biological sense. So this question on the left, this is a test question from one of the midterms. This question on the right is one of our SI questions from our worksheets. So if you want more of these practice questions from our worksheets, go ahead and go to the Google Drive that's linked in the iLearn folder, and it's all there. All right, cool. So let's go ahead and do this first one. The question's asking us, this is a chemical reaction, and let's say it takes a molecule and it breaks it down into smaller ones, right? So now it's asking us, let's try to figure out what's going on here. So we know it takes a molecule and it breaks it into smaller ones, right? And what does that tell us about the identity of the reaction? Remember that this tells us anytime we break a molecule from a larger to a smaller one, this is more of a anabolic process, or catabolic rather, sorry. So this is a catabolic process, right? And so remember that catabolic processes, they tend to have a delta G that is less than 0. So what else does that tell us? That tells us that our reaction can be classified as spontaneous or exergonic or favorable, right? All of those descriptors would be fitting for this kind of equation or this reaction. All right, so now let's go ahead and look at our answer choices. So one, we have delta G is greater than 0. So we know that wouldn't work because our delta G for a catabolic process has to be less than 0. All right, so we can rule that one out. Let's look at this bottom one, has an activation energy of 0. Activation energy is not really related to this question, and nor would it have an activation energy of 0, right? So all reactions will have some kind of activation energy for it to proceed, and this reaction is no exception, even though it is catabolic. Next choice, let's look at this one, needs no enzyme. That's not necessarily the case. It could be true that there's no enzyme, however, most reactions will need an enzyme for the reaction to occur, and this will not be the case either. And again, now we're choosing between, is it catabolic or anabolic, right? And we kind of determined that if we're breaking down large molecules into smaller ones, that's characteristic of a catabolic process, and it's not a catabolic one. Okay, so let's go ahead and look at the second one. This question is asking us which of the monomers that make up the macromolecules below would have the least energy stored in it, right? So these macromolecules have monomers, and now let's try to figure out what they are. So these are given macromolecules. For one, we have phosphatidylglycerol. This is a phospholipid. We also have myosin, which is a protein. We have chitin, which is a carb polymer. And we have polyethylene, which makes up some plastics made from ethylene. Okay, so now let's kind of figure these out. So phospholipids, remember that we have this like basic structure. And remember that the main part of the phospholipid that we really care about are these tails here. And these tails are hydrocarbons, right? And so these hydrocarbon tails, these are relatively large, or they can be. As you guys know, we kind of represent them in this way where we have just a bunch of up and down kind of lines. And they can be an extremely long molecule. So these are pretty big. Now we're looking at myosin. So a protein, remember that proteins are made of amino acids. Proteins are made of amino acids. And these amino acids, remember that their structure, you guys know that too, is this kind of repeating unit of an amino acid, which is that NCC motif. And then we have our carboxyl group at the end of the molecule over here, right? And we have an R group, right? So that's our amino acid. We also have chitin, so a carb. Remember that carbs are made of sugars, or sorry, carbohydrate polymers. So chitin in general, so let's say carb polymers are made of sugar monomers, right? And sugar monomers, these are carbohydrates, meaning the carbons are hydrated. And so typically you have a glucose molecule or some kind of molecule that looks like this, where we have a ring that looks like that, and it's 6 carbons long. Each carbon will have an OH group and an H group in terms of, let's say, this molecule, which is just a random one I'm drawing right now. Each molecule does have one of these. And so this would be an example of a sugar molecule that's 6 carbons long. And so this is like a general carbohydrate drawing. The big thing to take away from that is that it is a ring with an oxygen within the ring, and it's 6 carbons long. Next we have polyethylene, which is made from ethylene. And so ethylene, I'll draw for you right here. It's a very simple structure. It's CH2 twice, right? So let's now look at the question and let's see kind of what is it asking us. It's asking us which of these monomers has the least amount of energy. One way that we can think about this, and I'm going to do it down here, is larger, or molecules have bonds, right? Have bonds, and bonds equal energy. So let's think about it this way. If I have a large molecule, I'm going to have more bonds. If I have more bonds, I have more energy, right? Therefore, we're looking for, so if I have big molecules, I have increased bonds, therefore I have an increased total energy. Therefore, we are looking for the smallest molecule, right? The one with the least number of bonds in them that we can break. The reason why bonds equal energy is because whenever we break bonds, we release energy, okay? And so now let's look at these. Hydrocarbons are relatively big, right? Like we said, they can be extremely long carbon chains, and so we can rule that out pretty easily. Proteins, amino acids, these are 2 carbons long, right? But they have an extensive structure, especially if these R groups are pretty big. They are at least 2 carbons long with a nitrogen and 2 oxygen molecules. But for the most part, these are also considered larger. Carbohydrates, these are also relatively big. It's at least a 6 carbon molecule. And there's usually 5 OHs on it. And so that's also pretty big. And that leaves us with ethylene, which is a simple C2H4, right? It has a very small molecular weight. That would be, I believe, 28 grams per mole. And so if you're, kind of torn between polyethylene and myosin, or ethylene and amino acids, the one thing you could look at would be the molecular weight. Kind of check like which is a bit heavier, and that not necessarily tells you how many bonds you have, but it can tell you the relative size of one molecule to another. You can also count the number of bonds very simply. Ethylene has 1, 2, 3, 4 with carbon-hydrogen bonds and 1 between the carbons. However, in amino acids, for example, we have an N that has 2 bonds to an H, an oxygen with 1 bond to an H, carbons with 2 bonds to O's, carbons with other carbon bonds, carbon to nitrogen bonds, and the list goes on. And so the fact that ethylene has the least amount of bonds also tells us that it has the lowest amount of energy. All right, and if you guys want any more of this information, go ahead and go to your SI sessions or email them and do our worksheets, and we'll be more than happy to help. All right, see you guys.